I want to start off our 2-lecture series on alkene addition reactions by bringing you to the Unit 4 module. These Chapter 7 lecture slides. No, this isn't what I wanted to show you. But while I'm here, I think I might actually demonstrate this for you. This graph is an example of why different carbocations form. Here is an alkene. Would we call this a symmetric alkene or an asymmetric alkene? Maybe look at this one. Maybe that's better because that's a transition state. Asymmetric. Or maybe another term we could use is unsymmetric. It doesn't have the same substitution on both sides of the carbon. So an unsymmetric alkene. That means that it has two possible carbocations that can form a tertiary carbocation or a primary carbocation. Which is lower energy? Without looking at the graph. The tertiary carbocation is lower energy. It's more stable. It forms more readily. And the graph highlights that. The primary carbocation sits at a higher energy, requires more energy to form. The tertiary carbocation forms more readily. Either way, they both react. But if they both formed, we would predict two different products. One that has a primary alkyl halide, one that has a tertiary alkyl halide, and we only produce one product. That tells us we only produce one of those carbocations. We only produce the most stable. Okay, that was a good review on stability of carbocations. Oh, I see. I don't have the slides on here. I'm going to see if I can upload that for us quick because this will be good visualization, I hope, of all of the different reactions that we're going to cover. I hope this, yeah, here it is. I don't want you to copy this graphic because we're not going to learn all of these reactions. For instance, we're not going to learn the reaction that gives us a cyclopropane ring because it's too hard. No, it's just not covered in our textbook in this section, so we're not going to cover it. There's another similar one that actually forms a dichlorocyclopropane ring. We're not going to look at that one either. There's actually a couple of reactions not on this that we are going to cover. The halohydrin puts a halogen and an alcohol. We're also going to look at the haloether, which puts a halogen and an ether group. But one thing that we could do is make a graphic like this flowchart that just shows an alkene precursor and all of the different reagents that are required to get us to all of the different functional groups that we want. And then we could actually leave notes next to each of them about their regiochemistry and their stereochemistry. That's one way that you could organize the information about these reactions if you wanted to. What we're going to do is similar to what I showed you yesterday, where we're going to put up a generic example, which kind of resembles this. We're going to talk about the notes of the reaction, what's important to know about it, and then we're going to look at a couple of examples. One example that really highlights regiochemistry, one example that really highlights stereochemistry. We're going to try to get through all of these reactions as quick as we can today so that tomorrow we have time to practice and look at mechanisms for 4 of the reactions. This is one way that's really useful to organize things. But the other recommendation that I have, a recommendation that I have been giving to students that I've tutored for years, is to build a table of reactions. Now, I built a table of reactions when I started OChem 2, because I realized how many OChem 1 reactions there were that I couldn't remember, and just how important it was for me to review it and keep them all handy so that I could quickly organize them. In the years that I've been giving these to students, I've seen a number of different ways they formatted. I made mine on Excel, and that kind of allowed me to organize the rows alphabetically if I wanted to, and I could switch up how it was organized. I've had students that have handwritten their tables using rulers to make straight lines and making it very well organized. Other students that just kind of like scribble it onto a piece of paper and have some good organization. I've seen students that have made this on a Word document, and so that instead of having a real table, they just have different lines. Students that write it by hand, sometimes they put in their mechanisms with their examples. Students that do it on Word, sometimes they just have a picture of a mechanism. It's a lot of different ways to do this. It takes a lot of time, but without fail, every student that organizes their reactions in this way, takes the time to do it, rarely goes back to look at it. They hardly need it anymore. Because all of that time spent thinking about the reaction, what is important to know, how is it different from the other reactions, spending the time writing it out with your hand ingrains it in your mind better, so it improves recall, it improves recognition. Then, if they do need it, they have it, and they can go back and review it more quickly, or they can sell it for profit. My recommendation for organizing it is to put the functional group of your starting material in this column. For right now, that's going to just be alkene, and we're going to see all of these different alkene reactions. But later on in the semester, we're going to see alcohols and alkyl halides in here as well. When you get into OChem 2, you're going to see ketones, aldehydes, carboxylic acids. On the far right side, I like to put functional group of the product. The main idea here is, what conversion are you doing? You're taking what and you're making what? Are you taking an alkene and making an alcohol? Are you making an alkane? Are you making a diol? Are you making a carbonyl? Are you making an epoxide? Recognize the change. Recognize the functional groups, which means if you don't have your functional groups down now, get on it. Keep reviewing that. Don't lose track of those functional groups. It's the only way to organize all of these reactions and keep them separate from each other. So, for example, we're just going to have a bunch of alkene addition reactions. 2 of the products that we're going to make, or 3 of the reactions that we're going to make alcohols. But they're all different from each other. So then, in the middle, I like to put reagents and notes, things that you want to know about this reaction, things that are important to recognize. So, of all the reactions we can do with alkenes, 3 of them make alcohols. Rather than like spending the time to just put in all of these things, we're just going to say that the reagents look something like this for the 3 reactions. One of them just has 1 reagent. The other 2 actually have 2 steps. One of them is Markovnikov and it has a carbocation. One is Markovnikov and it has no carbocation. And one of them is an anti-Markovnikov addition. So you spend the time to build a table like this, you start to see the similarities between them, and you start to recognize why you want to take advantage of one reagent over another. Maybe you want a structural rearrangement to occur, or maybe you don't want a structural rearrangement to occur, or maybe you want to go with opposite regiochemistry. Do you guys have any questions on this? I don't offer any extra credit for it, but if you have not already made some sort of a study group in the class, now that we are less than a month away from the final exam, I recommend you start networking, talk with your peers, maybe even collaborate on an activity like this together. Maybe it's too much for you to do alone, but I guarantee it is not too much for you guys to do together. This is a really good exercise. It just takes a lot of time. All right? I apologize for how boring this next couple of lectures can be. It's really just kind of like info dump, but I'm hoping that I can help you organize it really well so that later we can do practice problems and you can just flip through your notes and quickly recognize what you're looking at. All right? Reaction number 1, HX addition, aka, anybody remember? Not, what'd you say?
Hydrohalogenation.
Yeah. Hydrohalogenation. So our generic example will have HX, where X can be chlorine, bromine, or iodine. And we'll add H, and we'll add X across the double bond. Any reason we're not using hydrofluoric acid? Yeah, it's incredibly dangerous, so no one really wants to work with it. Also, fluorine is not a very prevalent reagent or chemical in organic chemistry. So chlorine, bromine, iodine, these are our most common halides.
Does it matter that it's 2 or negative?
No, that's not really what it has to do with it. Its acidity is quite different than the rest of the hydrogen halides. Its reactivity is quite different. Yeah, it's just, I don't know why. It's not absent from organic chemistry. It's just not as common as these 3. Now, the regiochemistry of the HX addition, we describe that as Markovnikov. What does that mean? Yeah. Means the pattern is that on an unsymmetric alkene, where the 2 carbons experience different substitutions, H adds to the less substituted, X adds to the more substituted. The stereochemistry. Oh, sorry, you know what? Something else I want to know about regiochemistry, because remember, region kind of talks about the structure. This has a carbocation intermediate. That's important for regiochemistry. Why? Because if a secondary carbocation forms adjacent to a tertiary carbon, a hydride shift will occur. Or a secondary carbocation occurs adjacent to a quaternary carbon, a methyl shift occurs. Or if a carbocation forms adjacent to a benzylic position or an allylic position, rearrangements occur in order to form the most stable carbocation. So that's important for regiochemistry because it means I can have structural rearrangements. I might not actually add H and X to the 2 carbons of the alkene. X might add somewhere else after a rearrangement. The stereochemistry, this is random addition. That means that if 2 chiral centers are formed by adding H and adding X, they do not form with any dependence on each other, and all combinations of all chiral centers are formed. Let's do a couple of examples. Let's take 3-methyl-1-butene and let's react with HBr. We've seen this one, correct? What does this form?
One brother.
It does not form 1-bromobutane. Forms a carbocation on that secondary position. That's regiochemistry. That secondary carbocation rearranges to the tertiary carbon, and then the halogen adds to that tertiary carbocation. So we get 2-bromo, 2-methylbutane. Regiochemistry. How many chiral centers form in this product? Not one. Did the addition of the H form a chiral center? No, it formed a CH3. Did the addition of the Br form a chiral center? No, it formed an achiral carbon because that carbon's attached to two other carbons, two other methyl groups. So can I see the random addition of the chirality here? No, I can't. So let's look at example 2 to look at the stereochemistry. This time I'm going to add HCl. Talk to me about regiochemistry. Will the H add at one position or the other? Is there a way to follow Markovnikov's rule here? This is a symmetric alkene. So it doesn't matter where they add. You're just going to get H on one of them, Cl on the other. When H adds, let's say it adds to the top carbon, does it form a chiral center? It forms a chiral center at that carbon because now that carbon has the ring, the other side of the ring that is different, the methyl and the hydrogen. And when chlorine adds to the other carbon, does it create a chiral center? Yes. So what combinations of chiral centers can I have? Well, first, my hydrogen can add dashed on the top carbon, and my chlorine can add dashed on the bottom carbon. Are you confused why I don't have a dashed hydrogen? It's because that hydrogen can be assumed. But if you want to see the hydrogen, you just draw it in. Both the hydrogen has added to the bottom face of the alkene and the chlorine has added to the bottom face of the alkene. But the stereochemistry of these additions is not dependent on each other. So if the hydrogen adds dashed, the chlorine could have also added wedged. And there's no reason that the hydrogen has to add wedged, or excuse me, dashed. The hydrogen could have added wedged when the chlorine added dashed, and the methyl group could have added, the chlorine could have added dashed, wedged and dashed, and then of course my last combination is when both of them have added wedged. Two chiral centers are created, two configurations at both chiral centers. Their configurations are not dependent on one another. First, the hydrogen is added to make a chiral carbon, and it leaves an achiral carbocation, sp2, achiral. Then the chlorine adds and creates a chiral center. They're independent of each other. What is the relationship between these four products? They're all stereoisomers, but there are different relationships within that. Both wedged and both dashed, those are enantiomers. Wedged and dashed, those are enantiomers. But then all of the other combinations are diastereomers to each other. These are diastereomers. These are diastereomers. These are diastereomers. These are diastereomers. This one is in a great spot.
So all of these potential outcomes are really the result of the symmetric starting point.
Mm-hmm.
That's what allows all these different combinations to happen.
Yep.
Is that a general rule going forward? Not like an absolute rule, but like generally, if we start with symmetry, does that lead to more potential products?
No, not necessarily. No. What I want you to pay attention to when you're predicting a product, pay attention to the regiochemistry, if it's relevant, and pay attention to the stereochemistry, if it's relevant. I've given you two examples, one where only stereochemistry was relevant, one where only regiochemistry was relevant. Altogether, I think you guys would agree that this combination of the four products can be referred to as a diastereomeric mixture. Not a racemic mixture because I don't just have enantiomers. I have diastereomers that are forming. So let's look at a third example, one where we can combine the regiochemistry and the stereochemistry. This is, it's good, it's just a lot. Is there a place where Markovnikov's rule applies? Do I need to add H to one carbon or the other? They would both form secondary carbocations. So they can both react in the same way. So if you wanted to, we could change this by simply adding a methyl group right here to the carbon. Now, regiochemistry is significant. Before, I would have been able to add the iodine to either position, plus the iodine could have added wedged or dashed. Now, the iodine only adds to this position selectively. What stereochemistry does the iodine have? Well, first of all, it's important to recognize that the methyl group, that wedged methyl group opposite it on the ring, has no reactivity in this reaction. So its configuration stays wedged. But the iodine could add dashed, or the iodine could add wedged. Two stereoisomers form. Is it important that I show the stereochemistry of the hydrogen? No, because the hydrogen doesn't form a chiral center in this reaction. You guys okay with this? Only iodine created a chiral center. So I don't even need to show what happened to the hydrogen. It can just blend in with everything else. Cameron?
So in the starting materials, that methyl group that's there doesn't have a dash or a wedge, and then we have to specify that it becomes a dash or a wedge.
Yeah.
Because it goes from non-chiral to chiral?
Yes.
Okay.
Yes. If you draw this as a wedge or a dash, you lose points because sp2 hybridized carbons don't have wedge or dash stereochemistry. sp2 hybridized carbons, like this carbon, are trigonal planar. Everything it's bonded to is in the same plane. It's all flat. It's no longer trigonal planar, is it? It's no longer sp2. It's now an sp3 hybridized carbon, which means that it does have wedge or dash stereochemistry. I will say, though, that if you actually drew this as a straight line, you wouldn't lose points, so long as the iodine is shown with a dash or a wedge. And that's because you can now still see configuration. I think it's better to show it with the wedge and the dash when appropriate. I think it just helps us make sure that we're on the right track of understanding it. Okay, you guys ready for the next one? Let's look at X2 addition, aka halogenation. Now, some places that you look will include a solvent. Sorry, I should be a little bit more clear. A polar aprotic solvent. Something like diethyl ether, THF, which is also an ether, generic ether, etc. All sorts of stuff can be used there. Sometimes you will not see a solvent written. If you see a solvent like THF, it really doesn't mean anything. If you see no solvent, great. There's just less to distract you. The regiochemistry doesn't apply here. Actually, maybe the only thing that we could say is there is no carbocation. This is useful information because it means there will be no structural rearrangements. The two carbons of the alkene will become the two carbons of the halogen, of the dihalide. The stereochemistry for this reaction is not random. The stereochemistry of the two chiral centers, if two chiral centers form, is linked. We call it anti-addition. I do want to clarify a little bit about the regiochemistry. I said this before, the two carbons of the alkene both take on a halogen. That means that we can refer to this product as a vicinal dihalide. Not geminal. Geminal would imply that they are on the same carbon. And they're not just random anywhere across the molecule. They will always be adjacent, which we refer to as vicinal. This is different than vinylic or vinyl, which implies being attached to an alkene carbon. Okay, let's look at example 1. Let's take 1-butene again. I'm sorry, 3-methyl 1-butene. Let's react it with Br2. This becomes 1,2-dibromo 3-methyl butane. Only one chiral center forms. Would you agree? The CH2Br is not a chiral center. So this highlights that we form a vicinal dihalide, but it does not highlight the dependence of the chiral centers on each other. One chiral center forms, and because the alkene is flat, that chiral center can either form from the top or it can form from the bottom when these molecules are colliding and reacting. So I get both chiral centers. What's the relationship between these two products? They're enantiomers. Enantiomers are mirror images. So when enantiomers form, they form 50-50. They form a racemic mixture. Just taking us, I know I'm a little over the place, I apologize. Just taking us back a bit, these products were not enantiomers. They're technically diastereomers, despite the molecule being achiral. So they form a diastereomeric mix, which means they do not necessarily form 50-50. And that's because one chiral center remains unchanged throughout the reaction. All right, well, let's look at an example where we can see the dependence of the chiral centers. Let's do the same 1,2-dimethyl cyclohexene. Let's react it with chlorine. Yeah.
Just a quick side note, going back to what you were saying about the solvent. So we're assuming in all of these that a solvent is causing the separation between the two CLs?
No. We'll look at the mechanism for this, if not today, then tomorrow.
So,
And
okay.
it's actually the alkene
That's separating.
that separates breaks the halogen-halogen bond.
Okay, but that would be different than some of the stuff we've seen in the homework where it's like NaCl. You're assuming that that's an polar solvent that's pulling it apart.
Okay, so
And sorry,
NaCl is a salt.
right.
So all you have to do is dissociate the ionic bond. Solvents
have to be the
Solvents can dissociate ionic bonds. This is not an ionic bond. This is a covalent bond.
Okay.
Covalent bonds cannot be dissociated.
Okay.
It's like saying I have water, therefore I have H plus and OH minus. No, you don't. You have to break that covalent bond in order for that to happen. That takes a lot of energy. Something has to do that.
So what's going to happen here is that the electrons are going to,
Yep.
because of the nature of the electrons, that's going to break.
Yep.
Okay.
In fact, if this isn't too much of a distraction, I can even let you guys look at some of these reactions take place. If you are on our homepage and you come down to the external resources, you'll find this link to ChemTube 3D. If you go under organic reactions and then you go to electrophilic addition to alkenes, this is an example of the mechanism happening in 3D. And you can even just have this loop back and forth. It only plays one step at a time, but it shows you how bonds break and how bonds form. And then you can move to the second step, and you can have that loop back and forth as it shows you in each step what has to happen. Okay, so because the regiochemistry is not really relevant, I know I'm going to add a chlorine to both carbons. The stereochemistry is described as anti-addition. That means one group will add dash while the other group adds wedged. So if the chlorine on top adds dashed, the chlorine on bottom will add wedged. And if the chlorine on top adds wedged, then the chlorine on bottom adds dashed. And this is actually demonstrated by this step in the mechanism, where the second halogen bonds to a carbon directly opposite wherever the first halogen was bonded. What is the relationship between those? Are they enantiomers, diastereomers, identical, conformational isomers? They're enantiomers. You can't flip them, you can't twist them, you can't do anything that gets them to superimpose. So, because they're enantiomers, they form a racemic mixture.
Wouldn't they superimpose if you flip one of them horizontally?
Flip it like a pancake?
No, like a hamburger.
This way?
Yeah.
Oh, I see. No, because if you take this chlorine on the bottom that is pointing away, and you flip it, it's going to be on the top pointing towards you.
Okay.
It's actually going to look exactly the same as it does. Yep. All right, let's do another one. I'm going to be honest, I don't use iodine a lot in these halogenation reactions, but I do think it's a little bit worth seeing. That's it, that's the only product. And compare that to the same reaction with cis 2-butene. There, a racemic mixture of enantiomers forms. Are you concerned at all about the stereochemistry of the iodines in the second reaction? In a ring, sorry,
Is there strain because they're both in the same?
no. In a ring, groups that add opposite of each other, one wedged, one dashed, they can never rotate to not have that conformation. The ring is locked from rotation. It can do one chair conformation or the other, but it can't go all the way around. On a linear chain, you can rotate through conformations. Notice that your bond line is not the same here. This is how it started. But now the bond line is going up. So originally, this would have looked like this. If I rotate around this bond, if I just do a conformational change, this wedged iodine is going to rotate into the back so that it's pointing away from me. And it looks anti-addition. One adds wedged, one adds dashed. What I wanted you to point out was that here I have an iodine wedged and iodine dashed. But here I have two wedged or two dashed, given the other enantiomer. If it's anti-addition, how is it that they can both be wedged? It's because it's not the conformation it formed in. This is the conformation it formed in, and this is the conformation it rotated into in order to lower its strain. This is an eclipsed conformation, this is staggered. So this is how it forms, anti-addition, and it rotates into a low energy, what looks like syn addition. Doesn't matter what it looks like, it matters what it forms like. This is how it forms. Now, the iodine on the left could have been dashed, and the iodine on the right could have been wedged. That's the other enantiomer. Take for a second, if this compound were to rotate into that high energy conformation, now it looks like it's syn, although it isn't, because it's still added like this. This is how it forms. But if I look at its other conformation, what do you see? It's a meso compound. So, trans 2-butene only forms one product. It does not form a racemic mixture of enantiomers because it has no enantiomer. This product is meso. You can't see that unless you put it into this conformation. Cis 2-butene forms a racemic mixture of enantiomers that don't appear to be anti-addition, but when you consider the conformation they form in, you can see why they are chiral and why it's anti-addition.
When you have something that forms and then rotates around a single bond, is that considered two steps, or is that not a mechanistic step?
Not a mechanistic step. Nope. That is just the molecule you have made doing exactly what we saw molecules doing in Unit 2. They're just spinning around. I think I gave you guys this analogy that we need reactions to have a ton of energy in order to react. And also, when molecules have energy, they can rotate around their sigma bonds. They can go into different conformations. And at any given point in time, a larger percentage of your sample is going to be at lower energy conformations, but each individual molecule might be rotating. This molecule just is rotating after it forms. Okay?
So for it to be a mechanistic step, it has to have some sort of like bonding and electron stuff going on.
Yes.
Okay.
Rotations are not mechanisms. They are just,
That's just the molecule doing its thing.
yep, that's just a good depiction, a good understanding of what a molecule does. Yep. Okay, now I recognize I didn't give you guys a single reaction that has a diastereomeric mix. But the only thing that you need for that is similar to last time. You just need a chiral carbon that doesn't go through some sort of a change. And then you've got it. So if you guys are okay, we'll just move on. Yeah? Let's look at our third reaction. We're going to look at the halohydrin and the haloether addition. These are two separate reactions, but they are so similar to each other, it just only makes sense to put them together. I'm going to modify the way I've written this a little bit so that we can see the difference and the similarity between them. Over the reaction arrow, our alkene reacts with a halogen, X2, and with a polar protic solvent like water or alcohol. Water is a reagent that is a precursor to forming an alcohol, and alcohol is a reagent that is a precursor to forming an ether. All you're doing is just removing a hydrogen, increasing a bond to carbon. Water to alcohol, alcohol to ether. Are you guys okay with this demonstration? You understand it? If you have a halogen that is just in solvent, like THF, the halogen reacts. But if you have a halogen that's in a polar protic solvent, like water, or methanol, or ethanol, or rubbing alcohol, then the solvent also reacts. In terms of regiochemistry, once again, there is no carbocation, and you get this vicinal halohydrin or haloether, meaning, again, they're just right next to each other. In terms of stereochemistry, this is exactly like the halogenation example. These are anti-addition products. There is one important thing I need to add to the regiochemistry. And unfortunately, Markovnikov screwed himself on this one. He could have taken the claim for this one, but I can't because his rule is only about hydrogen and no hydrogen adds here. The alcohol, the ether, these add to the more substituted carbon. Jamie?
Does vicinal always imply one's going to be wedged and one will be dashed?
No.
No? Just on the same side?
No, vicinal just means next to each other. Yep. Anti is what implies one wedged, one dashed. All right, now in the examples that I'm going to give us, I'm just going to kind of alternate between using water and alcohol, but I want you guys to know that anytime I use water, you could swap that for alcohol and it would give you an ether version instead. Or anytime I use alcohol, you could swap it for water and it would give you an alcohol version instead. So let's take my favorite, 3-methyl-2-butene, and let's react it with water and bromine. We notice one component, the regiochemistry, we can see that the solvent has added to the more substituted carbon.
I know you mentioned when we were first going over reactions that what was over an arrow didn't necessarily matter if it was the steps.
Mm-hmm.
Here, is it assumed that whatever's below the arrow is the solvent?
It's just very common when there's only like 2 or 3 things to put. It's very common to just put the solvent on the bottom. But that's not always true. We're going to look at acid catalyzed hydration, and in that case, the solvent is often put on top, H2O, and the H3O plus is put on the bottom, which is technically the reagent.
But they're both reactants.
Correct. All of these are reactants.
But one of them has the label of being a solvent. That's because of what it does.
Well, because it is the most abundant reagent, you know. So you would run this reaction with like, if you're gonna do 5 grams of this starting material, you're gonna have like 20 to 30 milliliters of methanol. dissolving everything. That's all it's doing. Okay, does the regiochemistry apply in this reaction? Does it matter where the halogen goes and where the ether forms? It does. Because this is not a symmetric alkene. One carbon is more substituted, one carbon is less substituted. So where will the ether add? On the more substituted carbon. Does it matter what the stereochemistry is? The relationship between the halogen and the ether. Notice that in this reaction it didn't matter because the halogen didn't create a chiral center. Does it matter the stereochemistry between these two? It does. They both create chiral centers. So, if my chlorine adds dashed, then my ether forms wedged. And if my chlorine adds wedged, then my ether adds dashed. Whew. Now there's a number of things I haven't really highlighted for you guys. What about all these other functional groups that we have in our molecules, you know? Like, what if there's an aromatic ring? Well, aromatic rings are not alkenes, even though they have carbon-carbon double bonds. The aromatic rings will not react with these reagents. What if we have a ketone or an aldehyde? Luckily, these reagents are not reactive to ketones or aldehydes either. Carboxylic acids, maybe a different story, something we want to avoid. So what I'm going to try to do as we keep going and just keep diversifying our reactions is to show you what happens if other functional groups are in there and why those other functional groups don't react. Okay, you guys happy with this one? Great. Last example I want to give you guys here. Oops. Let's say that I have this compound that has a ketone, an alcohol, and an alkene, and I react it with halogen and mix it with halogen. Now you might think that this reaction is just going to do halogenation, that the alkene will react with the halogen and produce a dihalide, but there is an alcohol present. This will go through an intramolecular reaction as well. So the halogen will add to the less substituted carbon. The alcohol will attack at the more substituted carbon. In order to predict my product, I'm going to do mapping. I know that my alcohol is going to attack the more substituted position, and then this comes all the way back around. I didn't want to draw a 7-membered ring. Do you guys want to draw a 7-membered ring? I didn't mean for this to be 7 members. So I'm actually going to shorten my carbon chain. If you guys want to or can shorten your carbon chains, that's okay. Otherwise, just draw a 7-membered ring. How is it still 7-membered? What did I do wrong? Oh, I attacked the wrong carbon. I attacked the less substituted instead of the more substituted. It's going to attack at the more substituted carbon, and that more substituted carbon that the alcohol attacks at is connected back to the alcohol. This is going to produce a 6-membered ring where the ketone, as a reference, is position 4. Oops, I did that the wrong way. Five connected to 6, 6 connected to my alcohol, 3 connected to 2, 2 connected to my alcohol. 2 is also connected to this group out here, which is where the bromine is going to add. Would you agree that this is a vicinal halo ether? 2 adjacent carbons are bonded to both a halogen and an ether. It just so happens that this is a cyclic ether. It's a cyclic ether because it went through this intramolecular reaction.
And the second bromine is just not included.
It wasn't included last time either.
What's HBr?
Yeah, you're right. I haven't actually been doing very good at that. The HX addition, no byproducts. X2 addition, no byproducts. This reaction actually does have a byproduct, and the byproduct is HX. So here it would be HBr, here it would be HCl, here it's HBr again. So that's a good point. Thank you. What do you think? Intramolecular reaction, 6-membered ring, kind of fun. 7-membered ring, not as fun. So, okay.
If your alkene, like your carbon-carbon double bond, was like on started on carbon 2, like started on carbon 6, would that like make it impossible to form the ring or no?
If your alkene was too close to the alcohol, then it's not very likely that the alcohol would be able to come in due to the angle strain. However, not impossible. It's also possible that as one molecule is reacting with the halogen, the next molecule over is reacting with its alcohol. That would be more like polymerization, taking multiple of these units and connecting them to each other.
So if your double bond started on carbon 2 and went to carbon 3, would it form still a 6-member ring or no, a 5-member ring?
Good question. There are reasons why the alcohol attacks at the more substituted position. It attacks where it can stabilize the charge best. It attacks where the bond is the weakest. And the bond would be the weakest wherever it's the longest, and it's the longest because it's stabilizing the positive charge back. It all comes back to charge stabilization. But you have a good point on ring strain. If it had to choose between attacking a position that makes a 4-membered ring, that's more substituted, versus attacking a 5-membered ring, or that is less substituted, you could plot out the activation barriers. You could look at the energy strain required for that to happen and for the product that forms. You might find that they're pretty close to each other. So probably expect a mixture of products there. What
Those
is...
numbers are those are locations, not carbons, right?
They are locations. I'm mapping my atoms.
Okay.
The reason they're not carbons is because I mapped the oxygen as well.
Right.
And I wanted to map the oxygen because the oxygen is what bonds to the alkene carbon.
Would we see something similar to that on like homework, and we'd have to like make sure that we're saying that this is a location, this isn't a number of carbon? Is that like a common thing?
No, this is me giving you guys advice on how best to predict a product like that. This is not nomenclature, IUPAC numbering. This is mapping.
Okay.
This is figuring out what atom is where. And I think we have talked about mapping before. I think when we first introduced electron arrow pushing in Unit 1, I was like, we can just number these positions just to keep track of everything. You don't want to even tell me what it was?
Well, I see this bromine, like bromine 2, right?
Br2.
So it's Br2, so it's just...
Elemental.
Okay.
It's not the element. It's not like monoatomic bromine. It's elemental bromine. So it's how, yeah, Br bonded to Br. It's how bromine is found in nature. That's its elemental form. For instance, the elemental form of carbon is coal, graphite, diamond as well. The elemental form of oxygen is O2 and O3. Those are both elemental forms of oxygen. You never find oxygen as O floating around. You never find bromine as Br floating around. It's always Br2, Cl2, I2, H2, N2, O2, F2.
So we're not adding two bromines to this chemical.
To be fair, in halogenation, we did add 2 bromines. In halohydrin, haloether, only 1 bromine adds, the other bromine produces a byproduct. Yep.
So the second Br on that Br2 would do that same thing, just with another molecule.
No, that second Br leaves as HBr.
Oh, because the H comes off that.
Yeah.
Oh, okay.
Where did the hydrogen go, right? The hydrogen has to be a byproduct as well.
That makes sense.
Good question. Good.
Would we need to add that, like, if it shows on the exam?
I do often ask questions like, what is the byproduct of this reaction? And even without memorizing it, you can usually figure it out using critical thinking and stoichiometry. Right.
So if there was 2 alkenes in example 3, would you use both bromines?
Good question.
I know it would probably depend on where it was, but
Yeah, if there's another alkene in this molecule, there's a good chance that one of the alkenes goes through halogenation and one goes through haloether formation.
Okay.
At that point, there's a lot of things that can happen.
okay. I was wondering if how that would.
But you are right that you can take multiple equivalences of alkenes
Mhm.
and just add excess of these reagents and do it to all of those positions. There is one thing that I haven't shown you in this product. Are there any chiral carbons? Yeah, right here. Carbon 2 is a chiral carbon. So this product does form a racemic mixture. But it's not my favorite thing to show chiral centers inside of rings, so we can shorthand it like this. Okay, so far we have seen how to synthesize what functional groups?
Alcohols, ethers.
Hydrogen.
Hydrogen's not a functional group.
Oh, I didn't hear functional. I thought we were just going through hydrohalogen.
No, that's okay. We have seen how to synthesize alkyl halides, dialkyl halides, alkyl halides with alcohols, and alkyl halides with ethers. So in a way, we've seen how to synthesize alcohols and ethers as well. Next, we're going to look at hydration reactions. Now, I'm actually going to separate our 3 hydration reactions. So first, we're going to look at acid catalyzed hydration. Then we'll look at 2 other hydration reactions. The generic example here, take an alkene, react it with water and hydronium, H3O+, to add H and OH across the double bond. In place of H3O+, it's not uncommon to see H+ or H2SO4. The regiochemistry notes. This has a carbocation intermediate, and it follows Markovnikov addition. But to be honest, if I tell you it has a carbocation intermediate, it should be very obvious that it's Markovnikov, because that's what Markovnikov meant to say. Just like our HX addition reaction, this will follow random addition. There is no dependence on the chiral centers between where they form. how they form, rather. Can you name the product that forms? What adds here, H or OH? H. What adds here? OH. Methyl, 1-methyl cyclohexanol. That's our product. How many different structural isomers form in this product, in this reaction? Not 4 structural, 2 structural, and then 2 enantiomers of each structural isomer. I'm going to leave off the stereochemistry on this one. But I do want you guys to recognize in both places it would add wedge and dashed. And I'll be quite honest, it's very rare for hydrogen to add and create a chiral center. That really only happens when the hydrogen adds to like a tertiary carbon. The last example I want to show for this one should have actually been my first example. I like this one as my template, so I don't know. If you have it in your notes, I would have put this as example 1. I want you to go back and look at example 1 from the HX edition. Think about the product that formed in that example. Think about the difference between this reagent and the reagents we saw in example 1 of HX edition. Was the reagent in the HX edition an acid? HX? That's an acid. Because I think we use HBr, right? Hydrobromic acid. Is this an acid? Hydronium is an acid, yeah. It's actually a bad acid. I don't know if you know, you can't have a positive charge without a negative charge. So that might be H3O plus that's formed from HCl with water, or H2SO4 with water, or HNO3 with water. Anyways, is a carbocation going to form in this one? Did a carbocation form in the last one? Did a rearrangement happen in the HX edition? Will a rearrangement happen here? What is the difference between the product that forms here and the product that formed in our very first example today? Say it again louder.
What part that's what's up with
So instead of A, exactly. Okay, these are the 4 mechanisms that you will need to know for your unit test and for the final exam on alkene addition reactions. There will be more mechanisms in Unit 5. You will need to know the mechanism for HX addition and acid-catalyzed hydration. They are nearly identical mechanisms. Acid catalyzed hydration has one additional step, and you just differ what the acid is. Then you will also need to know the mechanisms for halogenation and haloether halohydrin addition. Those are nearly identical mechanisms. The only difference is that halogenation is one step shorter. 4 mechanisms, 4 reactions, 2 sets of 2. That's it. The other mechanisms are not impossible for you to learn, but I believe that if you master those 4, you would be able to tackle any other mechanism and be able to understand what's happening with it. So I want you to focus on those 4. Now I'm not going to go through those 4 mechanisms until tomorrow. So there's going to be a bit of time before we actually see them. I want to think about the rest of the reactions for the remainder of today's class.
I know you said it yesterday, but could you repeat why the OH moves to the left rather than staying on where the alkene was?
Yes. The OH does not add right away. In acidic conditions, the alkene acts as a base. When the alkene acts as a base, it generates something cation, carbocation. When carbocations form, they can very quickly structurally rearrange with carbons adjacent to them if it provides better stability. Here, that tertiary hydrogen shifts to the secondary carbocation, leaving in its wake a tertiary carbocation. That all happens before water donates its electrons from its oxygen to create a bond between C and L. So the reason that the alcohol adds where it does rather than to one of the carbons of the alkene is because of the carbocation intermediate and the specific structure we have here where that carbocation rearranges.
But if the adjacent carbon, so say there's one more carbon in between, it wouldn't move if it was equally substituted?
Correct. Similar to this, okay? So let's say we put a tertiary carbon down here at this position. It's primary now, but imagine it was tertiary, or benzylic, or allylic, adjacent to some other functional group. Carbocation can form here or here, both secondary. This carbocation will not rearrange to a primary carbon, and this carbocation will not rearrange to a secondary because there's no energy gain from that rearrangement. So even though there's something more stable on the far end, it's too far away for a rearrangement to occur. Great questions. All right, how are you guys feeling? I am hesitant to stop, so if you feel like you need to get up and move around, I don't want to stop you from doing that, but we're on a really good roll and I want to keep going. Our next hydration reaction is called oxymercuration reduction. You can call it oxymerc reduction if you want. 2 names for this reaction, which tells us it actually occurs over 2 steps. First, and I need a big arrow for this one. I always cut myself short. First, we react with mercury acetate and water. That's mercury acetate. I don't think you want to draw it out that long. So we can abbreviate acetate with OAC. Here's the O. It binds to the mercury. And this is AC, acetyl. Somebody's working with acetyl coenzyme A, right? Or acetyl, is it just acetyl A? I don't know how it works. Acetyl there represents this 2-carbon chain. You guys know acetic acid from vinegar. That's just this 2-carbon carbonyl. Acetaldehyde, 2-carbon aldehyde carbonyl. We're just abbreviating that with OAC. Second, we follow this up with a reduction step. Sodium borohydride. In that name, you hear the word hydride. That means H minus. Sodium borohydride does reduction because it is a reducing agent. It is the source of H minus. We're going to add H and OH. The H comes from the second step. The OH comes from the first step. Oh, some notes on this. Regiochemistry. This reaction does not see a carbocation, but it does give us Markovnikov addition. In terms of stereochemistry, this is yet again a random addition reaction. So the best example for us to see is what happens when 3-methyl-1-butene reacts. First, mercury acetate in water. See, I always cut it short. Followed by sodium borohydride. The product here was 2-methyl-2-butanol. Will we get the same product here? In order to get 2-methyl-2-butanol, I had to rearrange the carbocation. There's no carbocation in this mechanism. No rearrangements can occur, which means H and OH will always add to the 2 carbons of the alkene. Here, I get 3-methyl-2-butanol. That's its benefit. I really don't think it's worth going through too many more examples with it, because this is really, that's pretty much it. If we look at a similar example to example 2 from our first hydration, we still run into that same issue. If the alkene is symmetric, if the 2 carbons are equally substituted, you can't control the regiochemistry. You can only control the regiochemistry when the alkene is unsymmetric. My third method of hydration. Hydroboration, oxidation. I like these names, to be quite honest. They're not named after anybody, and they tell you exactly what each step adds. Oxymerc adds oxygen, the OH, and mercury in the first step. Reduction removes the mercury and adds a hydrogen. Hydroboration adds hydrogen and boron in the first step. Oxidation swaps out the boron for oxygen. Over the reaction arrow, once again, 2 names, 2 steps. If you don't have the 1 and 2 listed over the reaction arrows when you choose reagents, you've done it wrong. You can't mix all of these things together. They cancel each other out. They have to be done sequentially. First, borane, BH3. Also, very commonly run in an ether solvent, like with THF. So you'll see a lot of places that report BH3 THF. THF, not doing anything. It's actually intentionally doing nothing. It's inert to the BH3. Second, a basic aqueous solution of hydrogen peroxide. Basic aqueous solution of hydrogen peroxide. If you don't know already, hydrogen peroxide is an oxidizer. As a hydration reaction, this adds H and OH across the double bond. So then what's the point? Why am I doing another hydration reagent? Because my first 2 can only add the alcohol Markovnikov. This reaction is anti-Markovnikov, and importantly, there's still no carbocation. So the 2 carbons of the alkene is where the H and OH will add. Surprisingly, the stereochemistry for this reaction is syn addition. The H and the OH always add on the same face, both wedged or both dashed.
So why is that not vicinal?
Yeah, vicinal. Yeah, sorry. I guess the reason I don't say vicinal for these hydration reactions, like oxymerc and hydroboration, you don't see the H. So it kind of becomes invisible. But you are right. The addition would be vicinal. Yeah. All right, let's keep example 1 as 3-methyl-1-butane. Over the reaction arrow, I have borane and a basic aqueous solution of hydrogen peroxide. If you were to write any of the reagents in that second step, hydrogen peroxide is the most important reagent. Then again, the hydrogen peroxide concentrated isn't great. It's best if it's diluted. And the hydrogen peroxide really can't do what it needs to do until the peroxide is deprotonated. So all 3 are best. Hydrogen peroxide, excuse me. Hydrogen peroxide is the most important. So acid catalyzed hydration, 2-methyl, 2-butanol. Oxymerc reduction, 3-methyl, 2-butanol. Hydroboration oxidation, Will it be the same as acid hydration? Will it be the same as oxymerc reduction? Where does the alcohol at? At the least substituted. That'd be here. 3-methyl, 1-butanol. Do I need to show any stereochemistry? I sure can if I want to. I mean, those are tetrahedral carbons. I can show wedges and dashes wherever I want. There's no chiral centers formed, so there's no relevant stereochemistry. Let's take a look at this. 2-methyl, 2-butene. I react this with borane and hydrogen peroxide. Oh, it's not the one I wanted. I'm so sorry. Yeah, I want another carbon here. I need to make a chiral center. I wouldn't have created a chiral center otherwise. So 3-methyl, 2-pentene reacts with borane, then hydrogen peroxide. What group adds here to the more substituted carbon? H or OH? H for my anti-Markovnikov addition, which means OH adds here. And how do they add? Both wedged, both dashed, one wedged, one dashed. Not random, nope. They'll be syn, so either both wedged or both dashed. So if I don't see the hydrogen, if I only see the chirality of the methyl group, then I look at this and it looks like an anti-addition mechanism, doesn't it? Methyl group is wedged, OH is dashed. Is that anti? No, because the H is dashed. It's the H and the OH that have to have syn stereochemistry. Plus the enantiomer.
What happened to the methyl?
The methyl, it's right here. Yeah? If you're dealing with a problem where you need to pick the products and you need to pick the correct stereoisomers, you need to recognize what two groups are being talked about when we say syn addition or anti-addition. We need to make sure that it's the H and OH that add syn to each other. Doesn't matter what else appears to be syn. Deal? Okay, those are our 3 hydration reactions. From there, we're going to look at hydrogenation, or in other words, H2 addition. I don't think I made this super clear. No byproducts in acid-catalyzed hydration. There are byproducts in oxymerc reduction and hydroboration oxidation. I just don't think those byproducts help you connect the major products better. No byproducts here either in hydrogenation. The only important thing to know about regiochemistry is that there are no carbocations that form here, no structural rearrangements. And importantly about the stereochemistry, the two hydrogens add through syn addition. We'll keep our standard 3-methyl 1-butene, and we'll show how this just becomes 2-methyl butane. I'm back and forth. I really apologize about this. I'm going to give you a little bit more info about PDC. Palladium on carbon, or palladium on activated charcoal. The charcoal acts as a molecular scaffold. It creates a place for the palladium atoms or chunks to find the hydrogen molecules and the alkene, and for all of those things to react together. But the catalyst can be swapped with palladium or nickel, platinum or nickel. Nickel, palladium, and platinum are all in the same family. So they all have very similar catalytic functions. Notice here how in this example, the alkene is hydrogenated down to an alkane. In example 2, I want to highlight the fact that aromatic rings are not as reactive as alkenes. I also want to highlight the fact that multiple alkenes can be hydrogenated at once. It's kind of an ugly alkene right here, but might have made it worse. That's a diene coming off of an aromatic ring. The aromatic ring is going to stay the same, but the diene is reduced to an alkane. And I mean reduced there by oxidation state. This is referred to as reductive hydrogenation. I have yet to find any sort of oxidative hydrogenation. I don't know of an oxidative hydrogenation. All hydrogenations I know of are reductive. Now, there is some confusing things here because when you get into OChem 2, you're going to see that you can actually hydrogenate aromatic rings. You just need higher temperature, higher pressure. You can also hydrogenate carbonyls down to alcohols, but you need higher pressure, higher temperatures. Alkenes hydrogenate readily. Those of you that are in lab next week will hydrogenate a fatty acid. But carbonyls, aromatic rings, those don't reduce easily. They don't hydrogenate readily. I haven't yet given an example of the stereochemistry, the syn addition of them. So when we come in tomorrow, we're going to pick up here, look at a syn addition example. We're going to look at epoxidation, and we're going to look at oxidative cleavage. Then we're going to cover those mechanisms and do practice problems. My encouragement to you about that table of reactions is real. In the spring semester, I had a student who skipped Gen Chem 2. She took Gen Chem 1, she came in with Gen Chem 1 knowledge only. She thought she was going to struggle in the class. And when we got to this part, she really didn't have a lot of it practiced with reactions because you spend a lot more time thinking about reactions in Gen Chem 2. She built that table of reactions and I think got an A on the final exam. So it's a real encouragement to you. If you think that you just need a little power up to do well in this second half of the semester, take the time to start building that table. Start today if you can, or do it this weekend. The sooner the better. Okay guys, have a great day. I'll see you tomorrow. Happy studying.
So